control systems. So the approach for the control systems will be the combination of not only focusing for the gate, as well as we are intends to focus for the engineering services examination as well as for the PSUs. So in generic, that is a common sense. When you're able to crack the any kind of gate examination in the particular domain subjects, definitely you can easy to clear any other subjects or any other examination questions. Okay, so fine. First, focusing on the main theme, the gate related to the particular subject which we are taking here, about 2 marks and 1 marks. So we are able to get 3 2 marks and 3 1 marks. So usual case may possible to increase the question as compared to this one. So here sometimes in your textbooks or in particular private academies, they may classify the particular 2 marks maybe from a particular control systems or from a circuitry. So it doesn't mean that so control systems only getting 2 questions or one question from the 1 mark or 1 questions from the 2 mark. It's not like that, because when you exactly scrutinize the particular questions related to the control system, definitely will get 3 2 marks and 3 1 marks. So here in this case, if I would like to compare the difficulty level, because that's the usual case, what are the things we are going to focus and how many questions we will get. Okay, so it's around 9 to 10. So maximum will get 10 marks. So minimum you can guarantee for 9 marks. So this is what the usual case in the past 10 or 12 years. And comparing to the difficulty level, I will say it's easiest as compared to the other subjects, but not difficult as compared to the digital, right? So I can say it's the second easiest one as compared to any other subjects. So you can guarantee more than 90% of the marks in the control systems as compared to any other subjects. First one is obviously digital. Digital you can guarantee 100% marks, so there won't be any problem at all, because the systematic thing is which one you can guarantee the marks in the particular subject, that you need to focus more, because there may be some ambiguity in the questions or ambiguity in the understanding, right? Suppose if you ask me from the electrical side, so being an electrical and electronics engineering background, I will say there may be some ambiguity in the questions asked from the transformers or electronics, or sometimes maybe. So we cannot guarantee for the 100% of marks, and sometimes the difficulty level also so high, and we cannot exactly crack that question. So, but compared to the control system, so you won't get anything like that. So that's what the first thing I would like to make it clear here. And first one is obviously digital. So digital, there won't be any difficult question you could have get. Definitely you will get all the questions will be easy, and you can come out with a guaranteed marks. So the next one obviously control systems. So there are a predefined set of rules, a predefined problems, predefined topics. From this definitely you will get a question. So such a thoughts only we will have in the control systems, right? Okay, so that's what the case related to the introduction. And here the topics I would like to make it clear here. First, so here we will have first the introduction part, or we can say the black diagram or SFG. This is signal flow graph, right? So this is the first topic we'll have. Okay, so the next one is obviously a time response. I would like to make it clear what are the topics we'll have, and stability analysis, of course frequency response, in the final one state space model. Okay, so here the compensator design will be also come under the frequency response. Anyway, I will make it a separate topic as a compensator. So compensator design. Here we cannot say that we'll definitely get question from this frequency response, or we can definitely get it from the stability. It's not like that. Yeah, you will get a question from each chapters, but the 2 marks are 1 mark depends upon the difficulty level which IIT is setting the question paper. So we cannot exactly say that one, but obviously these are the basic chapters we have it in the control systems. So coming to the introduction part, okay, so basically uh, the basic terms we need to understand before we actually getting into the analysis part. Okay, so what are the things we are going to do it here in this control systems? The three things. Yes, obviously we listed all those things here. Okay, so why we need to term this input to output in terms of time? Basically, what kind of systems we are used to take in the control systems for any kind of things which I actually asked. So three things we are going to do it here. uh, any idea what are three main I think I can say objective in the control systems? The three main objective in the control system, so those things here listed. Yes, the stability under which category? Yes, okay, you're saying about what is that stability and what are the things we are going to do it, but the objective I'm asking, you're studying, you're okay, system stability or analyzing. So what you're predicting, first thing before we doing any analysis, what is the first step? Deduction. So synthesis or modeling is the first part in the any control system, right? First we need to model the system. First we need to model the system, then only we can do any kind of analysis or control part. What is the meaning of analysis? What is the meaning of control? Controlling the inputs for the output record. Of course, that is a third category. Usually that is what any standard textbooks, that is what they will list it out regarding to the control. So controlling the control process, anyway control is one of the process here. So system is getting controlled. What do you need to control? Controlling means, so controlling the input for the record output, controlling the input for record output. Here I can say the u of t is getting controlled. U of t you will vary, and u of t you will fine tune for the given c of t. So c of t is the record task which you want to obtain. For that you will fine tune the u of t. So that's the third one. What about the second one? That's what here we'll do. Analysis part. What is the meaning of analysis here? You are analyzing what? response. Analyzing the output. Response means output. So what you are going to analyze? You are going to analyze the output. So you're going to analyze the output by means of giving the input. So here input you will be controlled to get the output, but here you will analyze the what? C of t. You will analyze the C of t. Then generally the term analysis is applicable only for the output. You are analyzing the output. So any product, the analysis part is related to analyzing the output. So control is the term is applicable for controlling the input for the required output. And obviously these things, if you want to perform, what do you need? If you want to do those two things, if you want to perform these two things, we need a model, right? That is called as a synthesis. So modeling of the system or synthesis, I can say. So if you have the standard model, then only you can do these two things. Okay. So if you want to, so what is the meaning of these three categories? I would like to make it clear about this inputs, output, and the system. So what about the time? What about the system model here? What kind of model will pick here for any analysis or synthesis? What kind of model you will pick? So I've heard the word linear time invariant, dynamic, causal. So these three are the important property for the system. It must be a linear time invariant system that usually would have specified in the problem itself. So you no need to focus more related to this, because basically we are about to go for these chapters. These things might be important for your signal and systems. The signal systems only they will check. They will ask you to check out there is a time invariant or time invariant, causal or non-causal. So those things you will get a questions only from the signal systems. So I don't want to go for more in-depth related to this, to checking upon the static, dynamic, or causal, non-causal, time invariant and time variant. Right? Anyway, those things you will get it more problems related to this in that signal system part. Or generic, linear time invariant, causal. So okay, so, because I need to make it clear, because it will be helpful for my future questions to solve. So that's why I would like to take it and make it clear here. What about the dynamic? Static, dynamic. The dynamic system or static system? Dynamic. Why? With respect to input or time to time, it bound to change. No, the input and output are changes with respect to time. So that's a dynamic behavior. Static behavior, it's a steady state case. It won't be measured with respect to function of time, because there is no meaning of speaking about the time, because it's reached to the final output. So at any time the input or output is fixed value, then you will consider that as a static case. Here dynamic case, with respect to time, it going to be changes. So of t, function of t. If it is only u, then it's fine, but it's u of t, no. So it will be changes with respect to time. Like this, if you say, okay. Okay, so this is a one type. This is another one type. So this is a, so let us suppose consider this is with respect to time, and this is that input or output, whatever you can consider. So this is a fixed one. Irrespective of the time, the input or output is a fixed value. You don't need to specify in terms of time. But if you see here, observe here, at initial case, it is going to be somewhat lower. After some time, it reached some higher value. Again, it reached lower value. Again, it reached lower value. Again, it reaches to the some value point. So with respect to that particular time, the value is going to be changes. So that's why you're specifying that particular function with respect to time. Function of time. It's the function of time. So function of time speaks about the dynamic behavior of the input and output. What about the behavior of the systems? But how will you model the system? Okay, linear time invariant system, you said that, fine. It should be a linear system, that's an important case, but it must be a time invariant system. I'm speaking about the rule or the thumb rule for that particular system case. Why we need to specify that as a LTA system, linear time invariant system? Why it should not be a non-linear system case we are taking? We could have taken non-linear time variant system. No? Why we should take a linear time invariant system? If you won't take that LTA system, what will be the problems takes place? It's a basic fundamental related to the modeling of this. Output changes. Okay. If it won't changes, what will happen to the system behavior? If you take non-linear case, what will happen? Output cannot be predicted, but we can model. No, simple thing. If you want to say, it's a easy to design. For easier to design, first we will take usually a linear case. So here we are going to, in our general model, we are considering only a linear time invariant system. Okay, let us suppose consider linear system. Why we need to take a time invariant system? Time invariant system. So time varying input, time varying output, time invariant system. Also, we'll consider the system under the steady state. That's another one important thing. You must always keep it remember. So sometimes it may not be directly asked in the question, but you must remember this. Then only you can able to think to proceed the problem. So here, the input and outputs are time variant, but this case, the system which you modeled is going to be the LT system. It's a function of time of t, u of t, say r of t, whatever, and this is going to be a c of t. But what about the system which you model? It's a linear system only you're going to model, and it must be it is observed that it's a time invariant system. Because if you started to model, it's very difficult to model the non-linear case. The behavior which you're going to consider is going to be the linear behavior, and time invariant. Why we need to consider time invariant? Because it's a, I can say, simplest case when you're able to model the basic system. Why? If you start to find out the non-linear case, how much difficult it is. Non-linear easy or linear easy? So if you're able to fix the, you might have studied that in the numerical methods related to fixing of functions. So predicting the functions from the unknown characteristics or from the past historical data, you are able to predicting the future. How can you predict the future from the past historical data? From the past historical data, you must find out the function of input with respect to output. Then you will be able to get one particular case. Let us suppose consider you are taking only linear case. Let us suppose consider easiest one is straight line. We are considering only the linear case. Finding this one is easy, or finding something like you are fitting into the quadratic equation or cubic equation is easy. So because that complexity is going to be able to increased, but we are just taking only the basic case. We are considering that the output is linearly varies with respect to input. Okay, so output and input characteristics I'm speaking. So output is y and input is x, and we are just considering only it is going to be linear. So easier to fix once you know the slope. Let us suppose consider it's a linear one. So just if you find out only the slope, it's very easy to predict this function. The function may be like I can say y equal to something like 0.5, 0.5x or something, whatever it may be. And if you able to take the non-linear case, it's a linear one. Non-linear case, we need to make it as a linear characteristics. Then only you need to be able to find out the function. So these things you would have studied in numerical methods, fitting functions, and or else any problems related to your domain, finding the future from the past historical data. From the past historical data, if you able to find out the future, no, so such a case you will take this one, finding the functions for output and input. So that is the same case here. You excited with input, you got some output. Based upon that, you model the system. Why you model the system? I want to predict the output. I want to predict the output for a certain input. That's the same thing here. Here also I said the same thing. You have the data from 2000 to 2024. I would like to predict the data for 2050. Means you have data number of data for 2000 to 2024. I would like to predict the data for 2050. Likewise, for certain range of inputs, you have a certain outputs, right? Now I would like to predict the output for the input which is not excited till now. Okay, for that what will be the output you will get? For that I need to have the system model. Then if you have the system model, if you substitute that, you will get the output. Such a case only we are going to deal here. So need to understand why it is a linear time invariant system. So the dynamic is obviously correct, but a linear time invariant, how, when it will be modeled? So the input and outputs are always a time variant. Okay, it is not, you should not say any time that it is going to be under steady state. Under steady state, the term which is applicable only for one case, one thing, one parameter. What is that? For which one you will use the word steady state? The input and outputs are time variant. Okay, the system you modeled, no? Okay, feedback system or any gain, I can say any gain or any transfer function which you are modeling, no? The transfer function which you are modeling must be a model at a steady state. So the transfer function, whatever you are saying, no, that must be considered at steady state. Okay, so don't forget that one. The input and outputs are different. So whatever the things you are designing, that is going to be the different. You design considering that it is designed under steady state. The input and output are a parameter. The input and output are a parameters, and this is a system. So system will be designed under the steady state condition. So that's what I would like to make it clear. So let us consider it is H of S. It can be a G of S, it can be H of S, it can be M of S. Anything you can specify. So why it should be a causal system? Why it should be a causal system? It should be a dynamic system, okay? It should be a linear time invariant system, okay? Why it should be a causal system? Causal. What is meant by causal? So linear function time invariant means the system should produce the output for the same output for the same input, irrespective of time means when the input is given. Okay, so the system should produce the same output for the same input. So system will produce obviously the output for the input. The system will produce the same output for the same input given, but irrespective of when the input is given. When means what? It's a time condition. It will produce the output for the input, but irrespective of when it is given. So it can be, so it should not depends upon when you are giving the input. It should not depend upon when you are giving the input. That is what the time invariant. It should not vary with respect to time. So system should produce the output for the same input, but irrespective of when the input is given. Otherwise, you just make a note of it. The system The system must produce system must provide the same output for the same input for the same input irrespective of when the input is given. Caution. What about the caution? The general definition for a caution. The system output depends upon only the present and that's it. Correct. The system output should depends upon only the present and past. Now the system, I'm about to give the input, right? The output should depends upon the current input or the past input output. So the system may have the initial conditions. No, I'll tell you what is the meaning of initial conditions later. The system must also will produce the output for the initial energy associated with the dynamic components. If you speak about electrical, the dynamic components are inductor and capacitor, right? There may be some energy retained even after remove the power supply or even after you remove the input. Such a energy are able to change the output when you give the next time input. Next time when the input is given, the output is not same as zero conditions. But it is a complex to understand and complex to involve. That is why in a normal SISO model or a transfer function model, we'll assume that initial condition set to 0. Isn't it? So that's what the transfer function case. The transfer function is applicable for a single input, single output model. So right now we are speaking about only SISO model. So that MIMO is applicable for a state space model. So all this for all the 4 units will unleash the simple case only, the approximate model. So we will call generally the transfer function model as a approximate model, whereas the MIMO model, multiple input, multiple output model is a accurate model, where you can include the initial conditions of the system. But whereas in the case of transfer function, we are making that initial condition assumed to be 0. So initial condition, when something is there, when you are assuming that is 0, no, that means it's an approximate model. It's not accurate model. Why you are making it to 0? For example, V equal to L di by dt. Okay. When you just about to find out this is I. So this is a general way of we will take the Laplace transform. So we know that in inductor V is equal to L di by dt. When you are able to take a Laplace transform, so it's a V of S. Let us we consider it as I of S. Okay, it's V of S. What? So V of S, SL, I of S. But what is the thing we need to consider? We need to consider the initial conditions also. But general case, what you will do here? We just don't write that I of 0. We'll write yes. Just if you have one differential term, then you will write yes only. Yes into I of S into L. But that is not totally correct. So we must include the initial conditions. But for the time being, for the complexity, we are just assuming this is to be 0. That initial condition I of 0, initial at time t equal to 0, what is the initial current? That's what it speaks. I of 0 means what? At initial time, what will be the current? That current also you need to include when you're able to find out the voltage across the inductor. So that we are assuming to be 0, because when you involve more number of terms now, that will increase the complexity of the system design. So that's why you're able to make that initial conditions to 0. So that's what the transfer function. What is the transfer function? You know that LT of what is the transfer function model? What is the meaning of transfer function model? LT of output, LT of by assuming all initial conditions set to 0. That's what I am making it clear. So this is the assumption, right? By assuming all initial condition set to 0. That's what a general transfer function model. So if you take transfer function, it's just C of S by, I can say R of S or U of S, what it means. So the transfer function model, generally we are going to call the transfer function model as a H of S or M of S. It may be a M of S or H of S. So what are the transfer function model you are finding? You found out at the steady state. You design this under steady state. That's the first thing you must always remember. That's what I told you before we started that itself. So the input and output are time dependent, but the transfer function model is a steady state case. It is designed under steady state condition. Okay, so anything else? Okay, impulse input, that I would like to make it clear here. The impulse response of the system. What about the impulse response of the system? The impulse response, the response for the impulse input. So generally, what is the input at the time? The impulse input, impulse signal, you know, no? So what is the general nature of impulse signal? Okay, so okay, what about the impulse nature? How will you define that impulse signal? So impulse input, let us suppose. So at time t equal to 0, it will offer a 1. LT of del of t is 1. That is okay. If you ask me the Laplace transform of impulse signal, that is 1. But I am asking about the impulse signal. So the nature of impulse signal is most of the time, if you want to exhibit the testing conditions, we will go with the impulse signal. So that's why you might come across mostly the impulse response of the system in the problem. They would have specified in the questions the impulse response. Why? So because it's the most crucial play in testing the system. That input plays a crucial role in testing the system because it offers very high magnitude for a very short duration. That's kind of important dynamic phenomenon to test the system. So it exhibit the dynamic phenomenon in the input to test the system. So certainly the input shoots up and shoots down. So when you suddenly applied a very high magnitude to the system, how the system is withstanding for that input and how the system is performing the output. So that's a most interesting part in testing the system. So for that, usually most of the time we'll go with the system testing with the applying the impulse input. So the impulse input, it won't be available at any other time. It will be available only for a time t equal to, let us suppose consider time t equal to 0 or at very short duration. But what about the input magnitude output is going to be very high. Okay, so that's the general nature. So here, why I'm taking this one, because LT of del of t, you know that Laplace transform of del of t impulse signal is 1, and here when you're substituting, so what is that transfer function? The transfer function will be C of s, means the LT of, so what is that C of s? Output. C of s is what? Laplace transform of output at t impulse input, isn't it? Isn't it? So here, what is that thing? Okay, let us suppose consider what is R of s here? It is 1, and here it is the output at LT of output at del of t, isn't it? Because you are applying R of s as 1, because you might have applied LT of del of t, that is impulse signal, that is why you are substituting 1. So what must be the output at the time? It is nothing but output at del of t, but here you must apply it only in terms of s domain. So LT of output at del of t means the LT of output at del of t is equal to transfer function of the system. This is the main important condition which you must remember. So that means transfer function of the system is equal to LT of impulse response. Output at impulse input is what? Impulse response. Output at del of t means what? Output at step input, step response. Output at ramp input, ramp response. Output at del of t, impulse response. So impulse output means response, right? What is the input you are given? That is the prefix. What is the input you are given? Impulse. So output is response. So transfer function of the system is nothing but LT of impulse response. So generally basic. Okay, what about anything you would like to know about the basic parameters? Okay, what about generally system design? How it will be modeled? The modeling of the system. So you might have studied some in our academic. We had a syllabus related to the mathematical modeling. I cannot go and discuss in depth because it's not required for the GATE examinations. The basic idea of bringing the model from the basic system. How do you bring the mathematical modeling? Any idea? The force, torque, force, something you might have remembered. That's good. You brought something good. Mechanical system you model. Okay, let us suppose consider only one. Don't confuse with the too many things. So let us consider a rotation system or a translation force. It's an easy one. How you brought that output? Force கொடுத்தா அது ஏன் எதனால? Why you consider that cases? Applied force, you saying that something applied force is equal to something like m into d squared, some linear displacement, d squared x by dt squared, something b into dx by dt, something like that. You consider some k constant also, k into x, something. Why? I'm asking why you brought down that equation, why that equation came. Then only you can enter and we can write the equation, something equation written without knowing at least some meaning. Okay, so because of that, correct only. What you're saying is correct. Tell me. Mass into acceleration is equal to, that's correct. எப்ப மாஸ் அங்க எப்படி மாஸ் வந்துச்சு சிஸ்டம்ல, how you bring out the mass. So okay, let us suppose consider electrical system. Mostly we being electrical background, we can discuss in terms of electric. How the R came, how the L came, how the C came. We got only the output as voltage, let us be considered, and we are considering the current as the playing parameter. Current is a playing parameter to exhibit the output, and we substituting some RLC. Why? Why you considered R? Let me. No. I am asking. We brought some model, right? Or output or input. We are given some input. We got the output, and inside we are just putting one box as system, and in which we are just saying one resistor is series, and one inductor is in series, or one capacitor in parallel. How you brought out that model? Or let us suppose consider transmission line model. If you are electrical background, and even electronics background also, you know the transfer line and wave. There also you had a model, no? How you brought down that model? What is the synthesis? Synthesis is nothing but a modeling. The meaning I'm asking. Without knowing that basic relationship, we cannot just keeps on writing that s squared s. What is the meaning of that? And we know the d squared. Then only we can say why we need to take a Laplace transform. Then we can get into the problems. So we must always equate the input with respect to the output. That's a normal general logic. Energy balance equation. We are trying to meet out the output with respect to input, and the remaining what are the things are there. For that we are just associating or approximating or assuming some suitable effects. So something like in a, as you said, in a mechanical system, other than mass, we are considering a dashpot and spring, because the three major effects are assumed in the mechanicals are mass, spring, dashpot. Because there is a meaning for every component. Why they choosing a mass? There is a meaning. Why they choosing a dashpot? There is a meaning. Why they choosing a spring? There is a meaning. Because there is some acceleration effect will be takes place that will be proportional to the output. There is a rate of change of displacement that will be proportional to the output. The linear displacement may also proportional to the output. What are things are proportional to the output? Those terms associated with their suitable constant. Because directly if you say, let me consider f is proportional to 1 as plus 2 as plus 3. But all those three are proportional to f. But how will you replace in terms of equivalent? Something like some constant. K1 into 1, let me consider that first case. And K2 into 2 plus K3 into 3. So this K1 and K2 and K3 are, we are fixing and we are giving a name. So the effects, based upon the effects which you are assuming, we are replacing the constant. Okay. So this is my output. And I need to equate the output with the combinations of inputs. Sorry, the inputs are, okay, let me consider it's the input, because otherwise it will be confusing. So let me consider this is the input, because force is applied, no? Here in this case, force applied, we got the effects. So this is the input applied, and these are the different output effects. Let me say, if you want to say in terms of simple things, I can say this is output power. You know which one? No? This one, no? Windows India. SP. Okay. Thank you. First time handling now, so that I don't know. So let me consider this is the output power, and let me consider this is a something kind of core losses and kind of copper losses. If you want to simply understand in terms of transform, the total input power is nothing but a output power plus losses. There are two losses. One is core loss, another one is copper loss. Being electrical engineer, I'm just substituting this equivalent. Output is what are the input you given, that is converted in terms of heating losses, some reactive power losses plus output. So based on that, we just model the input output equations. So likewise, we also need to bring out some input output equations related to the problems which is given. Stroke erased, select erased. Okay, so coming to the problems, so we'll have some questions. Okay, so the first thing is easier one. So we'll let us take that one. So the first problem. Okay, before that I will tell you the another important introduction related to the systems. Directly before I'm going to the systems. See, this is E one of T. This is E not of T. Okay, so before we getting into this problems, I would like to make it clear related to the open loop and closed loop systems. That is also another one important things you need to compare. Though basics still we need to recollect. So what do you have in the open loop and what do you need to comment related to the why it's going like this? Will automatically go or என்ன பண்ணுமா? எங்க இருக்கு? Okay, fine. So open loop generally without feedback, closed loop with feedback. Coming to the first one important thing related to this sensitivity. What about the sensitivity of the system? Sensitivity is lower. Open loop sensitivity is lower. Here I would like to make it clear again. There is one typical rule which you must follow. Once you taken the Laplace transform, all the terms must be denoted only in a capital letters. It's another one thing. Before you taking Laplace transform, that function should specify in a small letter. That is not a problem. After that, you must specify only in a caps. So R of S. That's the difference between the before you taking LT and after you taking LT. So this is H of S, G of S, R of S, and C of S. Now you can comment about the sensitivity. So here system is, if there is some changes here, no, so there is some disturbance that will be directly reflected into the output or not. Sensitivity means what? Sensitivity to the disturbance. Sensitivity usually will measure in terms of other than the actual inputs or input variations. Two things. One is you are given an input right now to the system. Now, based upon the input variation, how the system will be sensitive, or else now you given the system because of some external disturbance or a noise, how the system is sensitive, how the system producing the output for that particular noise or disturbance. That's what the meaning of sensitivity. Sensitivity usually applicable related to the output changes for the other input given. Other input means what? Something like other than the actual input. Actual input 50 input magnitude கொடுத்துட்டீங்க. You're given a 50 amount of input magnitude. But after that, if there is some changes, that is called as a other than the actual input. Or something noise or a disturbance is coming over to the system. For that, how the system is response. System response means what? For this other variations or for noise and disturbances, if the system is not producing any output, it is insensitive. Our system does not sensitive for the noise and the disturbance. That's a good character. The system should not respond for the noise and the disturbance. As well as, for example, you varying the input but the system is not responding. Is that a good character? No. So both should be compromised. For the input change, if the system is not changing, that is a bad character. System should be sensitive only, but it should not be sensitive for noise and disturbance. So such a way system should be given. And coming to here, now you got it. Now I'm asking you to compare in terms of sensitivity. General nature, it's a simple one, easy to design, maintenance is free, and you will say here we have more components, complex one, complex to design, more maintenance, all those things that you will write. That is not a problem. But related to the terms associated with the control systems, first one is sensitivity. When you would like to compare in terms of sensitivity, so this is 100% sensitive. I can say a unit sensitivity. The changes will be directly reflected into the output. The changes directly reflected into the output. That is what usually we will call that 100% sensitivity or sensitivity with the unit gain. I can say 100% sensitivity is fine. Directly reflected, because we have only one single line, only one forward path, in which if you have any disturbance or noise, that will be directly reflected into the output. Okay, but here closed loop, what about the sensitivity? It's low sensitivity, or else there is two cases here: forward path changes and feedback path changes. Forward path changes and feedback path changes. The system sensitivity will be more for feedback or more for fallback? More for feedback. That's correct. The system, there is some big expression are there. It will take some half an hour time to solve all those things. After that, we will finally arrive. Okay, so we'll consider some parameter and we'll differentiate and we'll equate. So it will take a time consuming process, and it will finally conclude that the system is highly sensitive to the feedback changes than the forward path changes. Okay, the system is, this is the conclusion we'll have. System is highly sensitive to feedback path changes. Feedback path changes, then forward path changes. System is highly sensitive to feedback path changes than forward path changes. Means if the disturbance are there, that directly reflect into the output rather than forward path changes. What about stability? The open loop systems are always stable system. The open loop systems are always stable system. There is no meaning of speaking about stability for the open loop system. Stability is the word applicable only for the closed loop system, because the stability is affected only because of the feedback. That's it. So based upon the type of feedback, the system stability is going to be changes. Okay, so stability is affected by only because of the feedback part. Most number of time, positive feedback leads to unstable case, and negative feedback is preferred over the positive feedback for a stable system. Positive feedback is chosen for a system stability. Negative feedback is chosen for the system stability. Positive feedback, if is chosen, that may lead to the system to be unstable case. Okay, what about here? So we may have the positive feedback or negative. Here I chosen a negative feedback. What about M of S? It is G of S by 1 plus G of S H of S. Okay, in the case of negative feedback, G of S divided by 1 minus G of S H of S. This is for positive feedback and this is for negative. So plus sign will come for negative feedback. Sensitivity and stability. If anything is there, then and there I will tell you. Gain will be usually higher for positive feedback. Negative feedback, it will be this. Yes, ma'am. Yes, ma'am. No problem. Okay, coming to the fourth question, actually, in your 6.1, so as compared to the thing which we had discussed, so it was asked already in the gate. The feedback control systems are insensitive to both forward and feedback parameter changes, less sensitive to feedback than forward path, equally sensitive to forward and feedback, less sensitive to forward path, and high sensitive to feedback path. What we discussed now? Less sensitive to forward path than feedback path. So feedback path is more sensitive. That's what we listed here. System is highly sensitive to feedback path parameter changes than the forward path parameter changes. Okay. Okay, so we'll take into the first one. So what we need here, the transfer function. Okay. Easiest case, system related to the modeling. So that's a good one to choose the first this problem. So what do you need to do, ma? So here we are need to find out E naught of S by E1 of S. Is that correct? The transfer function is LT of output by LT of input. I just substituted, I replaced in terms of caps with the function of S because we are taking the Laplace transform. So what about the output? What will be the output here? The voltage across the capacitor. Voltage across the capacitor. What is the voltage across the capacitor? 1 by C. What is the voltage across the capacitor? V is equal to 1 by C integration over I dt. Okay. Now, how will you write voltage across the capacitor? Just will replace 1 by integration as 1 by S, no? 1 by S into C, it will be 1 by SC I of S. So what I can do, I can write down the numerator as 1 by SC into I of S. Then what about the voltage across the input? Sorry, I should not touch. Huh? What is the voltage across the input? The input voltage is equal to, just you can apply the Kirchhoff's voltage law. So what is that? L voltage across the inductor, L dA by dt. So L dA by dt now, how could you write? SL I of S. So we can take, okay, first we will write down here, then we can replace it. So I of t into L di by dt. Yeah? plus I of t into r. So r into I of t plus then that one 1 by c integration over I dt. So what will be the Laplace transform of this? I can take I of s. So I of s we can take it out commonly outside. So here it will be s term into L. So SL S into L plus R alone is there plus 1 by SC. So we'll have cancellation of that. I of s and I of s. If you just multiply with the SC, what you will get? S squared SCR plus 1. What are the options available? Otherwise, you can replace this one in terms of S squared format. What will be the S squared format? If you want to divide with the LC, you will get S squared format. So 1 by LC divided by S squared plus, if you divide with the LC, what you will get? S into R by L plus 1 by this. This is another one model. Either you can go with the S squared model or 1 by 1. Any one is the correct answer. So this is a given transfer function which is required as per the given problem. So any other problems related to this modeling, you can pick it out. சொல்லுப்பா இல்லை அடுத்த வாரம் தான். ஆமாம் ஆமாம் இருந்தாலும் தெரியல எப்படின்ட்டு சாப்பிட்டதும் இல்லை அந்த இன்டர்ன் போகாத பசங்க வர சொல்லு. சரி ஓகே சரி ஓகே 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 சரி ஓகே. So any other problem we have related to modeling? Okay, the second one, the unit impulse response of a unity feedback control system is given. So C of t is equal to minus t e power minus t plus 2 e power minus t is given as a response. Now you would like to find out the OLTF. So generally they not specified. If they just said a response and if you just take inverse Laplace of impulse response, that is going to be the transfer function. isn't it? That's what we given on statement, no? LT of Laplace transform of impulse response is equal to transfer function. No, you just check it out. Laplace transform of impulse response is equal to transfer function. If you take inverse Laplace, so if you take a Laplace transform of impulse response, what are you getting? Transfer function. Now if you want to find out the you have a response, if you want to find out the transfer function, just you have to take the Laplace transform, right? So take a Laplace transform of impulse response, you will get the transfer function. But what is the thing they specified? They specified the system is producing this response with the inclusion of unity feedback. That means what is the transfer function you are getting, that is going to be the closed loop transfer function. Now they will ask you the open loop transfer function. Okay, so that's the first thing. So if you have the response, impulse response, okay, so the Laplace transform of impulse response is your transfer function. Okay, now we have the impulse response. Just take a Laplace transform, you will get the transfer function. So minus t e power, what is that? C of t is given minus t e power minus t plus 2 e power minus t. So time greater than or equal to 0. Okay, fine. Now first find out the transfer function. So what you will get here? So generally 1 by s plus a is equal to e power, isn't it? So 1 by s minus a e power plus at. Okay. T power n. Good. T power n is equal to n factorial by, good, correct, s power n plus 1. Okay, this is the first one to remember, second one, third one to remember, fourth one, the combination of both t power n e power minus at. T power n into e power minus at, or convolution with e power minus. What will be the Laplace transform? N factorial divided by s plus a power, correct. Anything? What about by a by s plus a squared? S squared plus a squared, sorry, sin at. Sixth one. B s by s squared plus a squared cos at, correct. Seventh one. S plus a divided by, sorry, s plus s plus a. Okay. Correct. Correct. E power at correct? B by S square plus B square. Anything else is required? Everybody is not required. Never asked. That's no, it won't be asked. No, so that we will discuss later. If yes, when you're telling more number of things, no, at the time I don't want to confuse that. You would like okay, e power plus I and e power minus I. Yes, that's required. Not required right now. Sine hyperbolic, cos hyperbolic, it's not required right now. We'll discuss that later. If it is coming, then we'll discuss. Any other function which I must minus is sine. Only few things. Okay. Okay, so T. Oh yeah, this one is coming under this category. So what about for this one? 2 e power minus t is s plus 1, right? What about this one? 1 minus, okay, 1 s plus 1, 1 plus 1, that is 2. Okay, so if you take common factor of s plus 1 the whole square, it will becomes minus 1 plus 2 into s plus 1. Is that correct? So we'll have 2s, 2s by square plus, okay, so this is your CLTF. This is your, this you should not consider as a TF, it must be considered as a closed loop transfer function. 2 them plus 1 varma plus 1, correct? That's what I was. 2s plus 2 varum, so 2 no plus 1 will go. So this is not a OLTF, it's a CLTF, since they specified that response with inclusion of unity feedback. As per the given problem, they specified with the inclusion of unity feedback, the response was produced. Okay, so that must be the transfer function you obtained is not a OLTF, it's a CLTF. Okay, so now we need to find out the OLTF. What is the OLTF? Will you find out? So this is the general things we will do it. So if you want to find out OLTF from CLTF, okay, in the denominator, okay, just a minute. So generally, if you want to bring, so you don't need to do all those steps, because for example, you have a g of s factor, you have h of s factor. Now, what you will do? You need to put a g of s, then you need to put 1 plus g of s. Will have a numerator and denominator. H of s you need to multiply. Then after that, you need to take a common factor. You need to cancel out the numerator and denominator terms. It takes number of steps. Okay. So instead of that, what you can do? So just if you want to find out CLTF from OLTF, just write the OLTF function as it is. Then in the OLTF denominator, put opposite sign. So if it is a negative feedback, what do you have to put? Positive sign. If it is a positive feedback, you need to put the negative sign. Then what do you have to do? Numerator of OLTF, existing OLTF. What is the numerator? All those terms you just put, then you just multiply with the feedback value. What is the feedback value? That you just multiply. That's it. Or if you want to check, you can check it out. For example, 6 divided by s square plus 5s 5s plus 2. Let me consider. This is my g of s. H of s is, let me consider it is 4. Now what you will do usually? So if you want to find out a closed transfer function, g of s divided by 1 plus g of s h of s. So what do you have to do? 6 divided by s square plus 5s plus 2 divided by 1 plus 6 divided by s square plus 5s plus 2 into h of s is 4. H of s is 4, no? Now what you will get? 6 divided by s squared plus 5s plus 2 s squared plus 5s plus 2. So we have to take a common factor, no? So we will have divided by s squared plus 5s plus 2. Then you have to multiply this one, s squared plus 5s plus 2 plus 6 into 4, 24. Now this one and this one will be cancelled out. Finally, you will get 6 divided by s squared plus 5s plus 26. Okay. Now what I was said earlier, numerator into feedback value. Let me check it out. That one is coming around. So m of s I need, just I am writing the numerator as it is, divided 6 divided by s squared plus 5s plus 2. I am writing as it is. Then what I am doing, it's a negative feedback. Let us consider it's a negative feedback. So then only you will put 1 plus g of s h of s. Here also we consider a negative feedback. Most number of times you will consider only negative feedback. So negative feedback, now what I said, opposite sign. So it must be positive. Then what I asked you to do, numerator into numerator into feedback value. So what is the numerator? 6. What is the feedback value? 4. So 6 into 4, 24. So 24 plus 2, 24 plus 2, 26. Directly we can write now. How many times? How much time I have taken? How many steps I have taken? Nothing. But for this, for simple HFS is okay. Simple numerator okay. But if you have complex problems, no, complex higher order systems, at the time finding OLTF to CLTF, CLTF to OLTF is very tedious process. It will take more time. But it's the easiest one. We will get a defined value. So don't involve in complex step-by-step procedure. Go with the shortcuts or go with the simplest way. Okay. Likewise here, what I said, what we need here, so we are about to find out. Here the only thing is we just put the same sign here. If you want to bring CLTF from OLTF in the denominator, you need to put the opposite sign. Here, if you want to bring OLTF from CLTF, you need to put the same sign. Same sign na most number of times we are considering the negative feedback. Negative sign. Okay, here we are considering only negative feedback most number of times. So OLTF, if you want from CLTF, we need to put the same sign. If you want CLTF from OLTF, put the opposite side in the denominator. So if number, what is the CLTF here? 2s plus 1 divided by s square plus 2s plus 1. Then minus sign. What is the numerator? 2s plus 1 into feedback value is what? 1. So minus sign, if you multiply, what you will get? Minus 2s minus 1. What do you get finally? 2s plus 1 divided by s squared, that is your g of s. Within one step we can get it. Otherwise, what you will do? 2s plus 1 divided by s squared plus 2s plus 1 divided by, what you will do? How will you bring out g of s from m of s? Huh? Now, if you want to bring a open loop transfer function from CLTF, what will be the formula? M of s, g of s you need from a m of s. M of s divided by, forgetting, g of s by 1 plus g of s h of s, g of s divided by 1 minus g of s h of s for open loop to closed loop. You are bringing CLTF from open loop transformation. Now I am asking CLTF to OLTF. I am having CLTF, but I need a OLTF. M of s by 1 minus m of s h of s or m of s h of s minus 1. 1 minus, check it out once. Oppositely, yes. M of s h of s minus 1 or 1 minus m of s h of s. Because minus sign will change from that to this one. Okay, let me try with what you said now. 1 minus m of s, right? So 2s plus 1 divided by s squared plus 2s plus 1. What is the feedback? That is becomes to 1. Okay, what you will get? Yeah, we are getting that correct one. 1 minus m of s. So 2s plus 1 divided by this term and this term will be cancelled out now. If you cross multiply this one, you will get s squared plus 2s plus 1 minus 2s minus 1. So minus 2s minus 1 will be cancelled out. Finally, you will get s squared. Anyway, again you will take one more step, but we simplify. Okay, but don't go with this one. Try to go with this one. Within a single step, we'll get the answer. Okay. So means if you bring the CLTF from OLTF in the denominator, opposite sign. Good. Then the denominator opposite sign. Then what are the terms? Numerator of the OLTF term into feedback. What are the feedback? Entire feedback you need to multiply. Opposite OLTF from CLTF. The denominator minus, that means same sign, numerator of CLTF into feedback. Just make a short note of it as per your understanding. Okay, don't forget this. Then next one, a linear time invariant system initially at rest when subject to linear unit step input gives a response y of t equal to t e power minus t. Now that you can tell on your own. What about the third problem? Any soft copy is available here? Add page, Amma. Oh God. Whether it will be stored or not? Sensors, huh? Oh, sorry. Sensors. So third problem, given y of t t e power minus t. So what will be the transfer function? So we can directly take a Laplace transform of. Okay, but here they are asking actually the subjected to a unit step input. Subjected to a unit step input. So I think we can solve this problem later when we are going for a time response, because we need to know the step input S domain. So all those things we will discuss. So because without discussing that one, it's not correct to discuss this one. Okay, we'll go to the fifth problem, which is frequently asked in the examinations. What about the fifth one? Finding the DC gain. What is DC gain? What is the DC gain? DC gain means what? DC gain, or I will say it is a initial value. Initial value. DC gain or initial value. Initial value means what? What is the meaning of initial value theorem? That I will like to tell you right now here. The initial value theorem and final value theorem. Anyway, that we will discuss it during the time response also. What is the initial value theorem states? You would like to find out. Okay, let me first say value means related to output only. We are not speaking about the input, right? We would like to find out some values now, that is going to be the output value. So let me find out C of 0. What is the meaning of C of 0? Limit t tends to 0 when C of t, f of t, whatever. Now, when you changing to S domain, limit S tends to infinity, S into C of S. That is what? C of 0. This is the initial value theorem. Final value theorem. We would like to find out C of t at time t tends to 0. In a C of t, t tends to 0 is called as the initial value. And here, C of t with the t tends to infinite, final value. Okay, so here C of infinite I need to find out. So limit t tends to infinite at C of t, and here C of infinity will be a limit S tends to 0, S into C of S. These are basic things. These things everyone can do. Most, I won't say 90%, 100% people will know the initial value theorem and final value theorem. As of, if you're preparing for a GATE examination, 100% people will know about the initial value theorem and final value theorem. If you're not knowing, that is not my mistake. 100% I'm assuring, because being a faculty for past 10, 12 years, I know about the students' mentality when they're about to appear for the GATE examination. They know. Then what will make the difference? In 4 options related to initial value theorem and final value theorem, okay, definitely I am assuring all the 4 options will be picked by all the students. But I'm also telling that all the people know the initial value theorem and final value theorem. That's the beauty in the GATE examination. All the 4 options looks like a correct answer. For one perspective, A is correct. In another perspective, B is correct. In correct perspective, C is correct. But in another perspective, D is correct. Okay, so in someone's perspective, some options has a correct option, and they have picked that option. The IIT faculties usually when they setting the question paper, they able to fix the options also as per the wrong thoughts of people. How they will think, what about the wrong perspective of this question? All the perspective, if they solve, what will be the answer will come, that answer they will pick as options. They won't just like that pick A, B, C. They will put the correct answer, and they won't just like that pick the another 3 option. They will solve in the wrong way, and what is the answer coming, that they will pick as another option. Means if you stop about to solve in a 3 wrong perspective, all the 3 options will be exist in the gate examination. Okay, based upon my experience, I'm sharing this one, because initial stages I will come with the confidence. When I was writing the gate exam, I will come with the confidence that this option is correct, this option is perfect. But all those options, because I was solved nearly for a 20-25 minutes, and I'm getting the answer. When you're solving and when you're correctly getting the answers, which looks like options, no, then you will be proud of and you will say you are confident. But that answer is wrong. So that's what the usual way they will setting up the options. So coming to this one, when you need to apply the initial value theorem and final value theorem, that is a matter. So there are 3 beautiful answers will be there. Cannot be determined, 0, infinity. These 3 will confuse you most number of times. 0, infinite, and cannot be determined. Because for infinity also correct, cannot be determined also correct only. Because infinitive is cannot be determined only, no. But when you need to apply, which one is correct? Most closest answer. They'll say always most closest answers. Sometimes cannot be determined also correct, sometimes infinitive also correct. Because here for a final value, when I was about to discuss during the stability, but anyway, as the question is coming, I am just discussing now. Usually, the final value of an unstable system is infinity. Usually, the unstable system, the final value will be infinity. Unstable system, the system keeps on rising its output. Finally, it breaks down. Okay. Anyway, it's about to reach the infinity value. For unstable system, what will be the final value? On some occasions, they will say infinitive, and sometimes they will say cannot be determined. For a unstable system, means if they are about to ask the final value, what do you need to check? You need to check about the system stability. Directly, you cannot go and apply this one. Okay, if the system is stable, then you can go and apply this one. If the system is unstable, you can say cannot be determined. Okay, so that's the important thing. And initial value theorem, the initial value of the system are able to find out by this typical formula or rule. But when you can use this theorem, only when the system is proper. Stability is here. When you want to find out the final value, you must check so when you are able to find out the final value, you must check the system is stable or not. So when the system is not stable, definitely it won't reach to the final value. Okay, at the same you could not apply the final value theorem. So that is a separate thing. Related to final value, you must check the stability of the system. Test the stability before you check the final value. That is what you need to note it down. Check the stability before you check the final value. Check the stability of the system before testing the final value of the system. Check whether the system is proper or not before checking the initial value. Before checking the initial value, you must check whether the system is proper or not. What is the meaning of system is proper or not? So in a function, here let us suppose considering the transfer function, the numerator part and the denominator part. Okay, so usually the denominator part should be more than the numerator part. Or else I can say the pole should greater than the zeros. So this is an important condition to check the system is proper or not. Then only you can able to check the initial value. So check the system is proper or not before you checking the initial value theorem. Check the system is proper or not before you checking the initial value there. Coming to the DC gain. So this is this kind of question was asked more than 3 or 4 times in a different words. In a different words, they were asking about this conditions. What is the meaning of DC gain? First of all, DC gain. So DC gain nama gain at gain of the system at சொல்லுங்க gain of the system at zero frequency. Gain of the system at zero frequency. Okay. Here the S domain converted in terms of frequency domain. No? S domain can be converted as S will be replaced as J omega or J into F. Okay, approximately we can say J omega or what it may be. Omega is nothing but actually frequency. Let me consider approximately F. Okay, so all the S terms will have the frequency terms. No? All the S term will have the frequency term, right? When you substituting zero frequency means frequency as zero, means all the S terms should be substituted as zero. Okay, so that's the thing, simple thing. So DC gain, if you want to find out, just substitute S as zero in a transfer function. In a transfer function, S tends to zero in a DC gain. Okay, so here fifth problem. They given a M of S. The M of S as S plus 4 divided by S squared plus 7S plus 13. Okay. So what will be the DC gain for this case? 4 by 13 as a actual gain. So if they generally asking close to gain, close to DC gain, if they asking closed loop DC gain, it must be 4 by 30, isn't it? But what they asking? Open loop. So you must bring the open loop transformation. What is the open loop transformation? G of S. So S plus 4 by S squared plus 7S plus 13 minus S minus 4. Correct? So we will consider the negative feedback. We will consider the negative feedback. So what you will get? S plus 4 divided by S squared plus 6S plus 9. So this is your G of S. Now, if you want to find out open loop DC gain, so G of S, in a G of S, S tends to be 0. So you will get S plus 4 divided by S squared plus 6S plus 9. With S tends to 0, you will get 4 by 9. sixth problem, any idea? D squared y by the sixth one. The system is governed by the differential equation. Usually, the system character or characteristics are governed by the differential equation. So here you can see d squared y by dt squared plus dy by dt plus du, sorry, it's equivalent. Du by dt plus 2u. And u as the input and y as the output. So what do you have to do? Just take a Laplace transform. So s squared plus y of s plus s into y of s plus, sorry, is equal to s into u of s plus 2 into u of s. So you can take out y of s by u of s. So we'll have s plus 2 here and s squared plus s here. Simple problem solution. So what about the seventh one? Seventh problem. Again, they were asking about the transfer function. Del of t is a rotor displacement in radians. E of t is the output voltage. Kt is the tachometer constant in volt per rad per second. The transfer function of tachometer in terms of E of s by theta of s. So what will be the delta of t? So tachometer constant is what? Actually, this will be in volts because you need to consider about the units, right? What about the unit? So this unit is volt. This unit will be radian per second, right? Sorry, delta in radians. It's not omega. It's a radians. So it will be radians. So the tachometer constant is the delta of t is rotor displacement, that will be the denominator that you need to evaluate, and kf, sorry, k t up. So kt will be, so then what do you have to do? So kt is volt per radian per second. So this will be volts, this will be radians. So K1 tachometer constant. So that means output proportional to what? The voltage E proportional to what? That is what we need first to bring it out. We need to first write the equation, from that we can bring up. First we need to find out the characteristic equation. What is the characteristic equation? So they said E of t is the output voltage, Kt is the tachometer constant. Delta of t is the rotor displacement in radians. So output voltage is proportional to E of t is proportional to delta of t. Oh, delta of T is the rotor displacement in radians. So rate of change of displacement, no. So here, if you want to find out E, no, it must be a d del by dt, no, rate of change of displacement only you will get the voltage. Okay, so E of T must be proportional to actually d del by dt, then only you will get the voltage. So that is proportionality. So what about the tachometer constant here, kt? So kt you must substitute, now you will get the voltage. So this is volt per radian per second. So radian cancel, second cancel. Okay, now you need to substitute here, you need to fix a particular kt. Where you can fix the kt? Because here you must equivalent, no, the voltage must be equal to voltage. So left side you have voltage E of T, right side also you must get the unit as a voltage. How will you get? Because this is radian, this is second, but you need to get the voltage. How will you do that? So you must get volt by radian per second, then only you can get the voltage. So for example, volt per radian per second, what you will get? Because here already you have the radian per second. Because radian per second, if you divide that with voltage only, both will be cancelled, you will get the voltage as the same unit. Means you must substitute some unit in terms of volt per radian per second, then only this equation will be equalized. So what is that? What is the unit we have? What is the constant we have in terms of volt per radian per second? kt. K subscript of T, that should be multiplied with d del by dt. So then only it is balanced, because it is voltage, it's radian per second. This should be in terms of volt per radian per second. Then only radian per second cancel, and volt is equal to volt. Now we can find out E of S. E of S is equal to S into kt into del of S. See what they asking? E of S by delta of S. So it must be S into kt. Kt into S or S into kt. Option third one. So the eighth one we will discuss during the frequency response analysis. What about the ninth one? Ninth and 11th.
One reading per
2 or 1? Yes. You substitute a zero frequency. You're getting ninth one, no? So first you find out the ninth one. Two or four or one? Why two? Hmm. We're getting two or four or one. Anybody? Anybody else? Just substitute. You are able to find out the DC gain. So ninth one, so ninth one, they specified system output is 0 at which frequency? So T of okay S is equal to S squared plus 4 divided by S plus 1 into S plus 4, which must be the transfer function, and you need to equate the T of S value should be equated to 0 when S is equal to 0, or else we just replace this with omega, S as j omega. We can replace S as j omega and we can substitute that. So omega equal to 0. Sorry, omega we need to find out. Omega at particular frequency, that value will be 0. So omega we can substitute as omega itself. So this will be equated to 0. Omega squared j squared minus omega squared, no, plus 4 divided by j omega plus 1 j omega plus 4. But here the given as 0, output is 0 at the frequency. Okay, so they didn't ask you about the DC gain. Okay, means this is actually wrong. You should not specify this as. They didn't specify about the DC gain. Okay, they asking the frequency at which the output will be 0. Just reverse. Usually we will find out the gain value at 0 frequency. Now we need to find out frequency at 0 gain. We will find out 0 frequency gain earlier times. Now we need to find out frequency at 0 gain. Okay, now this will be 0 and omega will be the denominator. You just multiply with 0, you will get 0 only. So this will be 0 only. So omega will be 2 radian per second, because omega squared equal to 4, omega equal to plus or minus 2. So we will take only positive frequency, 2 radian per second. So read out the question clearly. Okay, they didn't specify the DC gain, so I was wrongly substituted that as 0, but that is not correct. We just substitute omega alone, because DC gain omega must be 0. It's not a DC gain. That's what I was confused. Yeah, they didn't specify DC gain. The system output is 0 at the frequency they asking. Okay, so 2 radian per second is the 9th one. Okay, 10th one we will go. What about the 11th one? 11th one, just go with the 11th. S square plus 9, S plus 2, S plus 1, S plus 2, S plus 3. So find out it's excited by a sine omega t. The steady state output of the system is 0 at. Now what is the steady state output? What is the meaning of steady state output? Steady state output means what? Actually here they should not specify this one. It's excited by sine omega t. Okay, no problem. Actually this problem sine omega t, later also we can discuss this one. Almost closer to this one. Sin omega t now itself you discuss now, that will confuse you, I think. State output. Magnitude terms, substituting the frequency. They didn't specify the steady state output, correct? But they specified any steady state output? The 11th one, whether they specified anything about steady state output? Excited by sin omega t. Steady state output, so omega t. But actually it's not correct. I'll tell you that. They must specify some frequency, like 8th problem, no? The input must be sin t na, then we can consider omega as 1. But in this problem, they didn't specify anything as omega. As plus, we don't know the magnitude. Because if you know the output, then we can just find out the magnitude. Then we can take the magnitude form and that we can do. Anyway, 11th problem, we'll do it later. Okay. So 11th problem is related to frequency response analysis. That we'll do it. What about the so 12th also related to time response analysis. Well, is related to control system. Okay. Okay, I will go to the signal flow graph. So the 9th and 11th problem, 8th problem also related to frequency response analysis. Anyway, it's wrongly included here. We'll solve during the frequency response analysis. The 16th also we can solve during stability analysis. 15th also related to compensator design. Okay, so all the remaining problems related to different chapters. Okay, so we'll discuss that later. So we'll move on to the second chapter, signal flow graph. Okay. Which one? 11th one. No, 11th is actually not related to this chapter. Okay. That's what I'm meaning. All these problems are related to different chapters. So directly, if I discuss that one, it will confuse you because we need to take the mandate form and we need to compare the input and output. So all those are related to the starting of frequency response analysis. So while we solving the frequency response analysis, we'll solve the 11th problem and 8th problem. And 12th related to time response analysis, error analysis. So that is also won't be opt now itself to discuss. Later stage we can discuss these forms. The order and stable and all those things again we are going to discuss through these stability analysis. Okay. So Mason's gain formula, I think you already know that. No need to discuss again and again. But only one terms I would like to make it clear here. Del K. What is it? K? What about the del? What about del? What about del K? That's what I would like to make it clear here. What about del? P1 on P22? Forward path, okay. PK is forward path. Yes. This is summation of one loop gain or individual loop gain. One means individual. One means sum of individual loop gain. Which one you need to sum up and we need to put it here in a P11? We need to find out the individual loops, one loops, and all those loop gains must be summed up and we need to place in the P1. What about P22? 22 means sum of gain product of two set of non-touching loops, two non-touching loops. Means first you need to find out the two non-touching loops. The two loops are said to be non-touching if it does not have a common, of course. You know the meaning of node, branch, input node, output node, source node, sink node, common node. All those things already you know. You don't have to discuss those things. So that is the important one. Where you can apply the Mason's gain formula? Can we apply between common node to the output node, input node to common node, input node to output node? Two nodes are there. So node which is having a incoming as well as outgoing branches are called as a common node. The node which is having only incoming branches is a output node. The node which is having only outgoing branches is called as a input node. Now this is source node or input node. This is sink node or a output node. This is a common node. Now Mason's gain formula, where we can apply? Mason's gain formula can be applied to find out the transfer function between source node to sink node. That is a common practice that everybody knows. In addition to that, what are the other places we can apply? Can we apply between source node to common node? Is that possible? Can we apply between source node to sink node? Yes, that's not a problem. Can we apply between common node to sink node? Can we apply between common node to sink node? Let me consider. This is okay. Can we able to find out directly the auth2 of s and y of s? Is that possible? Y of s by R1 of s is possible. That's not a problem. R1 of s is possible. This is not possible. But y of s by sorry. Just so R2 of s by R1 of s is only not possible. So this is possible. It's possible. R2 of s by R1 of s. What about R2 of s by R1 of s? Is it possible to find out? This is possible. This is only not possible. That's what I about to mean. R2 of s by R1 of s is possible. This one is not possible. Why? Any common node can be made as a output node, but any common node cannot be made as a input node. If a common node, this is a common node, this can be made as a output node, this can be a output node. Okay, this could not be a input node. Why? That's the reason enna sollama. We get to know why any common node can be a output node but cannot be input node. Any common node can be a output node but cannot be a input node. Any later stage can be removed, any previous stage cannot be removed. For example, in a thermal power plant, we can stop till you getting the heat, we can stop till you getting the steam, we can stop till you getting the mechanical energy. But by removing the steam, can we get the mechanical energy? Any later stage can be removed, but any previous stage cannot be. Previous stage remove பண்ணியா later stage கிடைக்குமா? But previous stage வச்சுக்கிட்டு later stage remove பண்ணிக்கலாம். That is possible. First coal combustion, heat produced, then we are getting a steam, then we are getting a mechanical energy, we are getting electrical energy. By cutting off the furnace, by removing the furnace, can we get the steam? By removing the steam, can we get the electrical energy? That is not possible. But by removing the generator, we can get till mechanical energy from the turbine. Purida? So till you getting the mechanical energy, you have the steam, you have the heat, but you will not get the electric load still, because that is a later stage. Okay, so the concept is we are possible to remove any later stages, but we could not remove the previous stages. So because, okay, let us suppose consider you removed the generator, till this point you can get the mechanical energy. Okay, let us suppose consider you are considering this as a input node, means you consider this is absent. If this is absent, how will you get this? That is not possible, no? By removing the heat or furnace, you could not get the mechanical energy. Okay, is it correct or not? So any previous stage cannot be removed, any later stage can be removed. That is the concept of the application of finding the transfer function in the signal flow graph. Usually we can find out from the input node to output node, that is a normal thing. But how we can find out the transfer function between the common node and the output node? That's the important thing. So that common node to output node is possible, directly is possible. Output node to common node, y of s by r of s is possible, directly not possible. Y of s by r2 of s directly not possible, but r2 of s by r1 of s is possible. Y of s by r1 of s possible. So y of s by r1 of s, we found it. Also we can find out r2 of s by, what do you get if you divide these two? If you divide these two, what do you get? Y of s by r2 of s. Means directly evaluation is possible, but finding two other transfer function, we can get the y of s by r2 of s. This is possible. Okay, so this is a way we need to find out that one. And I was asking you about del k. What is mean by del k? Del k, can you able to recollect what is the meaning of del k? No, not at all removing. Del k means what first? So this is gain product of two non-touching loops, this is sum of gain product of three non-touching loops, all those things you know. What is the meaning of del k? Pk means forward path gain. So P1 means first forward path gain, P2 means second forward path gain. What is the meaning of forward path? The path from the input to output, without crossing same node more than once. So you should not go like this. You crossed once now, that's over. Again you should not cross the same node and coming over to that node. Okay, that is not allowed. Forward path means the path from the input node to output node without crossing the same node more than once. You are allowed to cross only one time. all the nodes should be crossed only one time. More than once is not allowed. That's a forward path. So gains now all the gains what are there that should be cascaded, so we can multiply that one. That is not a problem. What is the meaning of del k? That's what the question. Because most number of times people won't remember and understand about del k. That's why I am giving stress to this. As you are aware, if you are already aware, you would have told. Now nobody is telling. What is the meaning of del k? Del k, okay, del 1. First we will get to know del 1 na enna, del 2 na enna. First, actually, what is the meaning of del 1? It's a del. It's a del. We have to find out del. For which one? This del is for big del. It's a whole system. This del is for the whole system. For whole system, how many individual loops are there? How many 2 non-touch loops are there? How many 3 non-touch loops are there? Those things we will do. Okay. What about del k? It will not be for whole system. It will be for a something closing. It's a part of the graph which is non-touching to the kth forward. Correct. If del 1 na, del 1 means what? It's the del for part of the graph. That means in the whole system, some part of the system will not be touching to the first forward path. You are chosen now first forward path. Anything you can choose as a first, anything you can choose as a second. For that particular forward path, some part of the graph in the system is non-touching to that particular forward path. That part you need to extract separately. That you need to bring it separately, and in that you need to find out individual loop gains, 2 non-touching loops, 3 non-touching loops. Okay, can you make a note of it? Del k, it is the del for del means del. This del you must put. Okay, this del. It is the del for the part of the graph which is non-touching to the kth forward path. It is the del for part of the graph which is non-touching to the kth forward path. That's the main important thing. N is number of forward paths. Okay. That's it about this signal flow graph introduction. When you get into the problems, then you can understand. I will solve one problem. Then we can move for lunch. Okay, you can look upon the first one. First one. First problem. Okay, I'll draw. Okay, can you tell me the number of forward paths and its gain? How many forward paths are there? How many forward paths? Direct one, blue color, first forward path, then through A, K, M, second one, then A, K, I, F, Y. So third one, huh? Fourth one, okay. Then anything else? I, E, and this will cross more than once more. A, K, I. If you're able to go in this way, you have to written in this way only. That is not possible. That is not correct forward path. You are allowed to cross the same note only one time. How many forward paths? 4. Is it okay? Or any fifth forward path is available? Check it out. Any fifth forward path is available? I'm getting only 4. 4 or 5? Look at the second forward path. Let me consider this second forward path. AKMG. AKMG. I'll tell you why I'm putting this bracket. Third forward path. AB or this one, no? AHFG, then AKMG, then AKIFG. Then fourth forward path, AB, ABD, DFG. I'll tell you why I'm putting this bracket. Okay, only 4 forward paths. What about the loop? 1 minus P11. 1 minus P11. What are the P11? How many loops are there? Infinite errors. This will come big. First loop, it's a direct one. And this is going to be the second loop. Then this is going to be the third loop. 3 loops, direct loops. And this will be the, sorry, this will be the fourth loop. Then any, so C, D, then MN, then this one IFN, four loops. Then anything else? No, not possible. Not possible. This one is. Any other loops? Check it out. Come on. Are there these 4 loops? Any other loops are there? M, M and N is over. I, F, N, I, F, M is not possible. This one is not possible. This one not possible. This one we already done. This one is not possible. You can check it out. This one is not possible. Here we have only one way, so we have to go this way. So here we want, and here we have only one. And from here we have only one. And if you go this one, come through this one, over. This one now cannot go this one. This one we no. So this one no possible to enter here. So this is not loop. This one is over. This one is over. And this one already we done. Any other loops? Any other loops exist here? You can check node by node. From node by node, you can check whether the loop is existing in that or not. So that is a final inspection. After the overview of the loops, we can go and check there are any more further loops existing by going node by node. So 1, 2, 3, 4, 5 nodes are there. So in individual nodes, you must check is there any other loops possible other than these 4 loops. If I'm checking here, something is going outwards, something is going inwards. So it is returned via any other path, then it's not possible. So from A, nothing is possible because both are going outwards. But from here, I'm checking it's going, but it is not possible to return via any other path. So from A, nothing is possible since all are outgoing. If something is incoming, then only loop is possible. And from this node, you can see one is incoming. So through this one incoming is possible. So another one loop is existing. So this loop and this loop is only existing because it is incoming, no possible. From here, this via this one is only possible. So only one, okay. And via this one, it's already existing. That's it. So this way, we already existing with M and N. So we can go and check with individual loops, then you will get it. So what will be the loop gain? C plus DE plus MN plus IFN plus what is the gain product of two non-touching loops? The two loops are said to be non-touching. Whether these two are non-touching, these two have a common node. What about this one and this one? DE and MN is both are said to be non-touching, and C and MN also non-touching. C and IFN also non-touching. So we must consider all this gain product. What is the first gain product? C and MN. Okay, this is the first gain product. The next gain product is C and IFN. Then C and MN and C and IFN. C and D is not possible. Okay. What about another gain product? Two non-touching loops. DE and compare with the other things. DE and IFN is touching. DE and MN is non-touching. Anything else? C compared with the DE, C is compared with the MN, C is compared with the IFN. Okay. Then D is compared with this one, D is compared with this one. D and MN only possible. And IFN is possible only with the C. FN is possible only with the C. Then MN is possible only with the D and C. That's it. Only three gain product. Okay, this we must add up. CMN plus CIFN plus DEM. Any three non-touching loops are there? Any three non-touching loops are there? Any three non-touching loops available? No. Only two non-touching loops are available. So this one and this one is touching. Okay. This one and this one is touching. This one and this one is two non-touching, but another non-touching should be existing. That is not possible. Three loops should be away from each other. Three loops should be away from each other. That is not possible. So that's it. Okay. So three non-touching loops are not available. Now we can go to the completion of numerator. What is the meaning of this numerator? P1 del 1 plus P2 del 2, P3 del 3, P4 del 4, since we have a 4 forward paths. What is the K equal to 1 to N? N is number of forward paths. N is 4 no here. So 4 now, P1 del 1, P2 del 2, P3 del 3, P4 del 4. What is the del 1? Del 1 is for the first forward path. Is there any part non-touching to the first forward path? Yes, some part is non-touching now. So this part is non-touching. This is touching, this is touching, all these are touching. This C is non-touching to the first forward path. So for this, we need to find out the del. What is the del? 1 minus loop gain plus 2 non-touching loops. But as there is only one loop, what you can do? You just find out only 1 minus. Means 1 minus C plus 2 non-touching loops. But 2 non-touching loops are there or not? We stopped up to this one because why we stopped here? No 3 non-touching loops. So we stopped up to 2 non-touching loops. But here we stopped from an individual loop gain itself because for the evaluation of this part which is non-touching to this first forward path, any 2 non-touching loops are there. Otherwise, you can just find this one. Okay. What are the portions which is non-touching to this blue color? Only this part. This line is touching or not? This branch is touching, and this branch also touching. This branch also touching. Only one part which is non-touching to the first forward path. That is this part. Okay. For this part, how many 2 non-touching loops are possible? No 2 non-touching loops are possible. Means only one loop is possible that I listed here. With this, the del one is over. Then what about the second one? Second forward path, AKMG. AKMG. So is there any part which is not touching? This whole part, no? This whole part is non-touching. What is that? C and D. So that means I can list out here 1 minus C minus D. No, actually within a bracket C plus D. If you just take out the minus, 1 minus C minus D and plus 2 non-touching loops are there. Is there any 2 non-touching? Only this part is available. Both are touching. So we should stop here. Then what about AKIFG? AKIFG. This is touching. So only C is available to find. So I'm taking first a big problem. So this is involves, if you start to find out the del 1, del 2, del 3 here itself, then the upcoming problems will be simple. So AKIFG. So only again 1 minus C. What about the fourth forward path? ABDFG. So is there any path available which is not touching to the kth forward path? This is available or not? No. This is available? No. This is available? No. So that means you should not put 0. 1 minus 0 only you need to put. Because somebody is putting 0, then the entire terms will be cancelled. That's it. So mainly the del 1, del 2, del 3 plays a vital role here. Okay.